Alright guys, so this project seems pretty difficult. I think we should, how we're going to do to split this up.
You guys started late.
Okay, so I've already divided up the topics between everybody. So Adrian, you're going to have chapter 1 and chapter 7. I'm going to do chapter 2, chapter 7, and chapter 10. And then Cristobal is going to get chapter 3 and 8. Daniel, you get chapter 4 and 8. Christopher, you get chapter 5, 9, and 10. I hope you don't mind, I gave you an extra one. And Jennifer, you get chapter 6 and chapter 9. So then from there, we'll just go ahead and I'll send you guys the specific sections and stuff like that.
Awesome, sounds good. Hey man, what's up?
Hey man.
Hey, so I got some questions about the topics they assigned us. I was hoping you can help me out with it.
Alright, let's see.
So, just confirming, nobody expects us to memorize all the molar masses, right? I mean, we can just look it up on the periodic table.
Oh no, you don't have to memorize them. So, after a while you will get used to them, you'll be like, oh, carbon's 12. Oh, nitrogen. You can go ahead and say, oh, it's 14. For the more complex compounds, so whenever you get like NaCl, something like that, you'll have to go ahead and add them together, and then you get your molar mass.
Okay, cool. And I also noticed that some periodic tables are more specific than others. Does that really matter?
It usually depends. A lot of the periodic tables are like, in the same ballpark. So if you round correctly, depending on the problem will tell you how and to what degree to round, stuff like that.
Okay, that makes sense. And this whole mole concept for chemistry, is that just saying how many atoms are present or something? I mean, what's it really mean?
So the mole is actually used for us to visualize the number of atoms so whenever we look at a periodic table, the mass is one mole of that element, if that makes sense. So then it's used to describe how it's a little bit hard to explain. It's such an immense number that it's used for us to wrap our head around.
Okay. Cool. And it's what, 6 point something?
It's actually 6.022
Oh, okay.
times 10 to the 24th. To 23rd, sorry.
Okay, cool. We'll write that down. I think that's everything that I was wondering. Do you have any questions, Steve?
I actually do. Let's see if you can help me out with these. So, stoichiometry, everyone thinks it's hard, and it's because of the mole, but now it's Avogadro's numbers in the gas laws. How does that work?
Well, remember, the mole is just a way to work with atoms. So, like, we're working with such large amounts of these really small particles. It just makes it easier to do calculations. So,
okay.
Yeah, it's just all to make it easier to do.
So the kinetic molecular theory, I have no idea what that is, man. I think I fell asleep through that part of the lecture.
Okay, so basically kinetic molecular theory takes all the gas laws together and attempts to create a simplified explanation as to why they all work. And that's the basic gist of it. If you want, you can go look up all the equations associated with it, but that's really all it is.
Okay. So I know that there are like trends on the periodic table, like electronegativity, but is there a way to tell by a certain element, or is it just a trend on the periodic table? That makes sense.
So there's no easy way to actually determine electronegativity. Basically, they found out those numbers by doing a bunch of experiments.
Okay.
But the general trend, though, is the further to the top and to the right of the periodic the more electronegativity.
So the most electronegative atom would be fluorine.
Yeah, exactly.
Hey Daniel, what are you doing?
Just appreciating some art. It's like a galaxy far, far away kind of thing.
Nice.
talking about appreciating things.
Mhm.
So we're studying the periodic table in Gen Chem, and I had a question. I wasn't too sure how the atomic radius increased or decreased. So can you explain that to me?
Yeah, that has to do with like the valence shells or electrons for the atom. So you could kind of think of it like here's helium, here's francium, and you go down the group and to the left, that changes the size.
Will it increase as I go down and left? Okay, that makes sense.
Yeah, right?
It's kind of like this picture. There's
like
nothing
nothing,
here,
and look at that.
and there's one.
So Leslie, which group on the periodic table does not like to react with other chemicals?
Okay, here, let me pull it up so I can show you. Okay, this one's kind of simple because the noble gases are the group that do not like to react. Why? Because they're what we would like to call a happy family. Because all of their outer electron shells are full, which means that they do not need to react with other elements. All of the other elements are trying to acquire in full outer electrons so their shells can be full too to achieve the happy state, you know?
Oh, okay.
Does that make sense?
Yeah, it makes
Yeah.
sense. So I have another question. What is the Riemann equation used for?
Okay, I can see how that's kind of confusing because the Rydberg equation is used to predict the position and the wavelength of just about any line a series is given.
Oh, okay. That seems simple.
Yeah.
So I know the first two postulates from the Bohr model, but I can't remember the third one. Can you tell me what it is?
Yeah, for sure. The third one is always the hardest to remember for some reason. So all you have to remember is that an atom can change to a different stationary state only when it absorbs or emits a photon. I can never pronounce that.
Yeah, it's
Sorry. The energy that the photon equals the difference in the two states of the energies.
Oh, okay.
Does that make sense?
Yeah, it's better than from where I started.
Yeah, it kind of confuses me sometimes too. Like, I don't.
And I also don't know what the VSEPR is. Can you tell me what it is?
Oh, okay, well, yeah. For starters, it stands for balanced shell electron pair repulsion. And it just basically is a model that is often used in chemistry for the geometry of individual molecules, just by the number of electron pairs that surrounds a specific molecule in the central atom. So, like, in order to minimize the repulsion of this group of valence electrons, it's located as far away as possible from others around the central atom.
Okay.
Did that make sense?
Yeah.
Okay, good. So, like, do you have any other questions?
No, I think that was it.
You're good?
That was kind of difficult to for the test. So.
Yeah. Okay, well, since you're here, can I ask you some questions?
Sure.
There's just some things I don't really understand. And I'm really confused about what we went over today in class. Like, how do we know how to set up the problem, and where do we start when we're doing all this stoichiometry things, and like, how do you know what cancels out?
Okay, so first you find what the problem wants and what's given to you based on what comes on the problem, right? And then you make a roadmap towards the answer that you need, and then you cancel the units by putting them across from each other. Like say you get grams, you put grams over one, and then on the next one you get the grams in the denominator, and that's how they cancel out.
Oh, that makes sense. Okay, so like for this question on the review, I didn't understand how to work out the problem. But do we have to memorize every single conversion factor? I mean, there's a lot of them, and I don't know which ones are more important.
I guess from what I know is that the ones that are most important are the length ones, but you don't have to memorize them. They're usually given to you in the problem, so you don't have to worry about them that much.
Okay, so, okay, did you do this one? Because I was looking at it and it's a bit tough to wrap my head around it. So it would really help me if you could explain what the difference is between energy and matter.
Okay, so the main difference between the two is that energy is produced from matter, and matter is something physical, like something you can see or touch. So that's the main difference between the two.
Oh, okay. That makes sense.
Okay, guys. So did everybody do their research?
Yeah.
Yeah, I think we're done.
Okay, let's get ready to start this.
Yeah.
Yeah,
Let's get started.
may the force be with you.
Dude.